of the course. Okay, so for this fourth lecture, we're going to speak about Markov models and see a little what are the properties of those models. Okay, so what are the goals of this lecture? So it's first to understand what are Markov models, how they are created, and what are they made for, be able to manipulate them, so get all the ways of computing probabilities for sequences emerging from Markov models, estimating them, etc. And see also what are the properties which are implicit, which are implied when we are thinking about a Markov model. And we will do that by studying a few examples of application of those models. So the first example will be really very, let's say, made-of example, like what we do for probabilistic model when we think about dice or coins. Here we'll make up example where we generate Markov models. So just to, let's say, justify what is the what are Markov models made for? So until now, we only thought when we had observation from a probabilistic point of view, we only thought they were independent and identically distributed. So usually you call that IID. Okay, and so when we have those discrete values, like what we did for the project with DNA sequences, or if we have text, we have Bernoulli or multi-Nui model, and all our observation, they are independent. So there is, you see, like we used to draw this links of dependency. There are no dependency. All the points are next to each other. But as you guess, of course, it's not always the case. And very often we record series over time. And there is a direct dependency. So we can think about many examples. I just wrote a few here. So when people are drawing something with their hand, depending on the letter you're drawing, if you just record the angle of what you're drawing, there will be, for each letter, there is a characteristic form. If you're drawing a O, you see the change, the relative change in angles are always the same. When you're tracking people or tracking things, there is a dependency between what we are tracking. And there is also a very simple example. If you think about financial market or the weather, the weather or the value of a stock option at a given date influences the value that this option could take in the future. Okay, so and the past, let's say the past of stock option will influence how the stock option will change. And of course, and this is what I'm usually interested in, but that's not all. When you're working with text or genomes, you can think that the letters or the context has an influence on the next letter. And here, this is a simple example of representing this type of dependency. On this graph, the author took the origin of species from Darwin and first counted the occurrence of letters, of all the letters. And so you see there is, it's not a uniform distribution. You have some letters which occurs more than the other. So the E is the most common of the vowel in English. And you have some other consonants which are more occurring more often than the others. But it's not all of it. It's just the letter occurrence. And you can use this information when you want to crack a code, for instance. That's the first trick you would do. You would use, if you have a code which is a one-to-one, you can use the frequency of the symbols and try to match them with the letters. But if we try to move a little, we can look at the what are the succession of letters. So that's called bigrams for text, and record the succession of letters. And you see if you write that as a matrix. So here it's the number of times E is followed by a space. Or here you have the number of times E is followed by an N. Okay? And you see that this matrix, if there will be no dependency, this matrix should be all the rows should have the same value. But of course, it's not the case. Depending on the letter I'm just seeing, the possible letters are heavily biased. And when you look at that, you really you can make up already a few the typical preposition. If you have an A, it's easy to see an N, a R, or a T. And if you have, let's take the T. The T can be at the end of the word, or very often after the T you have an H because of V, etc., etc. Okay, and so you there are many cases where you want to take into account dependency, and Markov models will be the, let's say, the simplest, the first step. Oh, sorry, I put the example a little too early. The Markov models are the first step, let's say the first layer of models you can do if you want to move away from independent observation. So what you will do, you will just say, instead of throwing my result independently, I will do like I do for those big grams, depending on what I'm observing now, or maybe a little in the past, but this horizon will be really limited. That will determine what is happening in the next step in the future, okay? And that's only that. So we just move away from independence to a dependency which is limited in scope, okay? And we will see that's relatively easy to manipulate, but that's already allowing us to be a little more powerful when we are treating with series data. So I will start. So you get the idea now, and I think the matrix you saw, this will be a guiding principle, this matrix of succession of events. But to see a little the model from the example, I wanted to start directly with an example where we have a mouse which is in a maze, a labyrinth, and the mouse starts in room 1, okay? And we will monitor the process we are looking at is in which room is the mouse, and the mouse can every time the mouse changes of room, it's one step in our process. It's one new observation. So we just monitor the room of the mouse, and every time the mouse is, we just think the mouse is going randomly, and so for each room, every time she's in a room, she has the same chance to go to all the rooms she can access from the room she's in. So here, if she's in room 1, she has one chance out of 2 to go to room 2, and one chance out of 2 to go to room 4. If she's in room 2, you see there are like 3 doors, so she has one chance out of 3 to go to the other room. Okay. And so we can, let's represent a little the space, our state space. So all the possible states we have now when we're looking at this process are a number of rooms, so from 1 to 9. And you see that there are 2 rooms which are a little special. So there is a room with a cat. So when the mouse enters the room with a cat, she gets eaten. So she will not move anymore. And there is another room with a cheese. And when she enters the room with the cheese, she got her reward, so she will not move anymore. And so what can we do now? We represented all the possible states we have, all the possible room allocation for our mouse. So we can start to describe, if I'm in room 1, I can draw that as a graph. I can just go from room 2 or to room 4, and I have a probability. I can write that on the edge of 1 out of 2. And that's the probability for the mouse of going from 1 to 2. Okay, if I'm in room 2, I have 3 rooms, just as I said, and my probability is, for instance, going from room 2 to room 5 is 1 out of 3. Okay, and the same in room 5, it's the only room with 4 different rooms that we can access. The probability is 1 out of 4, and so we can fill up this graph of room to room, going from room to room. Those are the probabilities of moving at each step from a room to another one, and we can very easily represent that as a directed graph, which is a little, if you worked with that already in computer science with string, it's like an automaton. I mean, it resembles a lot an automaton. And as we always need to be able to move, you see when we are in room 7, so I made a mistake. In fact, now when we are in room 7, I put outgoing links, but when we are in room 7, we don't move anymore. I will correct that on the slide. Sorry, I just noticed I made a mistake. So this and this and this and this. So when those one are wrong, I'm sorry. So okay, when we are in room 7, we just stay in room 7 here with probability 1, and when we're in room 9, we stay in room 9 with probability 1. And so there, I drew the graph a little too fast, and so we cannot move back from room 7 to room 4 or room 8, and the same from room 9. Okay, but you can see here the process. So what will be the observation? We observe the room in which the mouse is. So first room 1, then let's say room 2, and then room 5, and then room 2, and then room 3, etc. So this is the observation we have. And at each time, the mouse forgets in which room she saw before, and the probability of the next room will be only determined by the current room. Okay, and so we have this way of seeing our succession of states, and that's exactly the idea about the Markov chain. Is the observation we have at a given point in time. If we think about this observation given the past, in fact, this will this will only depend on the present. So that's the first order Markov chain. You can, of course, you can increase a little the dependency here. That doesn't change too much. You just speak about second order Markov chain or third order Markov chain, but we'll stick to that for a moment. It's enough. So the probability, the distribution of position at times t only depends from the position at times t minus 1, so from the previous one. And it's a very general model for temporal or sequential processes. So we just need to, you see there is a slight difference. There is the state of the space of all the possible states. We call that the state space. It's discrete. And then we look at discrete times, succession of times. That can be, of course, time series, location of mouse, but that's also really commonly used for sequences of words or sequences of letters. Okay, and so let's go and just compute now from our example of the mouse. What is the probability of the mouse doing exactly this path? So going from 1 to 9, given not that she arrives in 9, is the probability that she goes 1 to 2, then 2 to 3, 2 to 5, 5 to 8, and then 8 to 9. So it's so she's doing this succession of paths. We can think of this trajectory as going through this graph. So we just go from 1 to 2, probability 1 out of 2. Then we also have to go from 2 to 5, it's probability of 1/3. From 5 to 8, probability of 1/4, and from 8 to 9, probability of 1/3. So the probability of going through one trajectory, I'm doing, it's not formal now, I'm just doing the intuitive way of computing this probability. You see, we just conditionate, we just go through this graph of states, because that's the only thing we need to know, so where we are. So we move through the graph and we follow the links, which are those conditional probabilities. So these probabilities, so 1/2 times 1/3 times 1/4 times 1/3. If I didn't do a mistake, we have 1/72. Okay? And so that's the probability of a path. I think with this description, and this is when we have this graph with all the values on the edge, you see that's a very that's like a description. Sorry, I have a problem. That's a description of the Markov chain. Okay, so we can So we can write. Wait. So sorry, I'm moving on just to rewrite now how did we compute that? How would we compute that with a more formal way? We can say the probability of observing all my sequence from x1 to xl minus 1. If I'm using base formula, the probability of having all those joint events, I can conditionate the last point by all the past, okay, and then do the same again with this point given the past, etc. But you see here, so by doing conditional successive conditioning, but here, because of our Markov property, having the last point given all the past just simplifies, and we don't need to count. We don't need to take into account the previous observation to decide what is this value. And so the probability of a sequence under the Markov, this Markovian assumption is just the probability, the product of the probability of moving. So here I did the conditioning this way, going from the last to the first because it's easier for Bayes rule. But when we read it, when we computed it the first time, we went from the beginning to the end. So the probability of the first letter times the second letter, like the first sequence, the first event in the sequence, times the probability of the second event given the first one, times the probability of the third given the second one, etc., up to the end. And so it's just the probability, the product of the probability of transiting from the current state to the next one. Very simple. And it's kind of summarizes to what I just showed you here. It's like moving on the graph. Okay, so having the graph is a compact way of representing the this directed graph is a compact way of representing the Markov chain. But what we can do, and we will see this will be the practical way of working with that, is that we can write also the adjacency matrix with the weights of the graph with the weights, and this is equivalent to that. So I have this graph here. I just write a matrix which has in row and in columns as many rows and as many columns as the number of states. So here I have 9 rows and 9 columns. And I write here the value I have on the link, which is also the probability. So here, if I'm in on this element, I'm in row 2, column 1. It's the probability of going from state 1 to state. Sorry, it's the probability of going from state 2 to state 1. Okay, and that's what is written here by the general formula. It's just a little confusing to see because of this conditioning, but the AST, so the ST element of the matrix, is the probability of going from S to T. Okay, so I drew here to recognize a little the matrix, and so you see here where I did a mistake. Hop, those are not there. Here, if I'm on row 7, I can just go back to in state 7. I just go back to state 7. So the probability is 1 from 7 to 7, and we can take. I made a mistake here also. So yeah, that's the problem. If I have to write 91 cells, the chance of making a mistake is high. So if I'm in 1, 2, 3, 4, 5, I'm in state 5. I can go to state 2, state 4, state 6, or state 8 with probability 1 out of 4, state 2, state 4, state 6, and state 8. Okay? So I think that's relatively, let's say, intuitive. And we will see that this matrix is in fact very practical, because we will just be able to resort to a traditional linear algebra calculation to compute probabilities once we have this transition matrix. So what are the parameters? As we said, we just need to know now with Markov chain what is the probability to go from one state to the other. But we also need, when we compute the probability of a sequence, we need to know the distribution. What is the distribution for the first observation of a sequence? So in the example here of our mouse, the mouse always started in room 1. So this probability is set to 1 for this first observation, and it's 0 for the other one. But we could think of course, any type of starting distribution for the first observation. Okay. So we saw with the example now the first properties of this Markov chain. And this is where I moved forward. So what is the probability of observing a given sequence? And I went through that shortly. And as we saw, the probability of observing a given sequence is just the probability of the first element in the sequence, then multiplied by the probability of seeing the successive events. So it's very intuitive. So now, let's look at something that's starting to be a little more interesting with Markov chain. Be a little more interesting is that we want to know what will be the behavior of our chain if we wait a little in time. So we don't know what happened in between. So because our end goal here for this example of the cat, the mouse in the maze, is to know what has the mouse more chance to end up in the cat room or to end up in the cheese room. I mean, at some point when she's arriving in one of those two rooms, she will stay there. So she will always end up in either the cat or the cheese room. The question we ask is, so is it more likely that she will end up in the cat room or in the cheese room? And what's the probability? And that's something we will see we can easily compute with Markov chains. To be able to do so, we first need to know, can we compute the probability of having non-consecutive event? So if I want to go, so now let's imagine for two steps. So if I want to compute the probability of going from room 1 to room 5, what is this probability? Here I have two possibilities. So either I go from room 1 to room 4, and then room 4 to room 5. And that's this probability here, 1 to 4 times 4 to 5. Or I go from room 1 to room 2, A1, 2, and then from room 2 to room 5, A to 5. Okay? And, sorry. So you see here, we just combine, in fact, to go from one state to the next one. We would sum over all the possible states that will be in between and take the product of the probabilities. And so you will have to work that a little in detail, maybe on paper. So I didn't write that as an exercise, but what's happening? I could do so if you like, but you can easily show that the transition matrix, the probability of going from state I to state J is just the transition matrix A to the square, just because of basic linear algebra, and taken at row I, column J. So what does it tell us? It just tells us that, in fact, if I'm looking at the process where I don't go from one step to the next one, I do K step in between, like here, 2 steps. So the process of looking at the mouse every 2 rooms, every 2 moves, it's also a Markov chains, and this Markov chain has for transition matrix simply the power, the square of the transition matrix for the elementary states. And that's a very, very strong property. That is what is making our life extremely easy when we work with Markov chains, because now we can directly know if I'm increasing the time, if I don't have too many states, I can just compute powers of my transition matrix. Once it's specified, and I know what is the process, in K step. So it's a little, I mean, one needs to work a little with it to get used to that. We will do that with the exercises. But that's one of the strong properties. So we have a Markov chains, and the transition matrix is simply a to the power of k. And so what's now we can solve in a very computational way our question of what is the probability that the mouse will get first to the cat or to the cheese. So here I draw like that, but that could be any path. And what can we do? We can just say at some point the mouse will always end up in one of the two rooms. So I can just take various powers of A to see what is the probability. So I take various powers of A and I combine. So this is my, this is the, having two steps, okay? So that's my matrix A of transiting between two steps. I can combine that with directly with my initial probability, which is 1, 0, 0, 0, 0. And you see in this case, that just corresponds to when I do the matrix product of this row vector times the matrix. I'm just taking the first row of these powers of A. Okay, so maybe. And so we can take the A to the power of 2. We can see here, after two steps, I can either get back in room 1, and this will be 1/3. Be in room 3, this will be 0.16, because you see there is only one path to room 3. Be in room 5, there is more chance because I have two ways of going there. And I could already be in the cat, and I have no chance of being the cheese. I can take, when I increase the power, we see after 4 steps, some rooms are so, and the probability of the cat or the cheese little change. And when we increase the power of A, at some point you can see after 100 steps, I either landed in the cat room or in the cheese room. And so we basically computed that there is 60% chance of being in the cat room when we end up, and 40% chance of being in the cheese room, just doing this matrix power. Okay, so of course, so there is more chance that the mouse will finish in the cat room. If we look at the configuration of the maze, we see that it's kind of expected, just because from where the mouse started, from the beginning, there are already more paths where the mouse could end up here. Okay, but so you see, this is the Markov chain is a good way to try to see what's the behavior in general when we start to have a lot of states. Okay, and so so the main question we have now with Markov chain, we know how to look, how to compute probabilities of trajectories, how to see what is the behavior after a certain amount of step, and we saw here on this special case where, in fact, in this for this Markov chain, we have two states where the mouse arrives, it just gets absorbed here. We can, with powers, understand where the mouse will stay. So what we would like to do, to be able to do, is to characterize what are the behavior of those chains. So here there is a clear behavior. We get either stuck or in cat or cheese. But in other more general case, what are the typical behaviors of Markov chains when I wait long enough? So what is is there an equilibrium of a chain? Does it ends up, is there chains which can have an equilibrium where somehow the process will not change anymore? And can I understand this equilibrium? Before being able to do that, we just need to have to describe two small things about the Markov chains, in the sense, oh, wait, okay. We need to describe a little what are the different structure we could have for the chain. So as you saw, we have graphs, and those can imply, depending on the link and the structure of the links, this can imply certain things. And there are two structural properties which one needs to keep in mind with Markov chains on a discrete state space, so with a finite number of states, is that so we can have some part of the chain that imply dead ends. Okay, so in our example, this is what we had. those states are called absorbing. Okay, because the cat and the cheese room, we could not go out of it. Okay, so this is the case when you have absorbing state, your chain. No matter what you do, if you wait long enough, you will end up in one of the absorbing states. Okay. But if there is the contrary, if we can always reach all the states, so if there is always a way to get back to a state after waiting some time, and this is a nice property, we say that the chain is irreducible. Okay, and that's a relatively good property because that's just where we can work. We can say that in this chain we will always be able to get back to some space. And there is another thing which is it's not really important, but it's good to know that can occur, is that we can have some states because of the configuration of the links that are periodic in the sense that I can only get back to them with a certain with a multiple of a certain amount of path. So for instance, here, if I'm in state 1, oh, come on. If I'm in state 1, I let you check that here, state 1, 2, 3, 4, they have period 3, 1, so on. Sorry. The horror of home office. So, so you can see here, if you're at state 1, no matter how you do, you will always need to do a multiple of 3. So 1, 2, 3, or even if you branch in 4, 1, 2, 3, 4, 5, 6. So the number of steps you need to get back to state 1 is always a multiple of 3. The same for state 2, the same for state 3, the same for state 4. So this chain, when all the states are periodic, if you take the I don't know, you say that the smallest common divisor of all the periods, you can say that your chain is periodic. Here it's a chain with period 3. If it's not the case, your chain is aperiodic. We will rarely, if never, look at periodic chain, just to keep in mind that, of course, if there is a period, this has a strong effect on the way my chain behaves after a long time. Okay, but so we will most of the time look at a periodic chain. So now that we looked at those two properties, so very easy. So there is, if I take any two states in my chain, I can always get back to it in a finite amount of time, a finite amount of step with a positive probability. And I don't have periods. So let's imagine this chain is well behaved. So it has these two properties. Then what Markov chains are telling us, and this is what we'll see with observation, but that's something you can relatively easily prove by working with the matrix form of a transition matrix. Then there will be a unique distribution, mu, so it's a distribution of the state, such that when I'm in this distribution, so if I draw a state with this unique distribution, this distribution mu, and I apply my transition, then I'm still in mu. So I'm in stationary distribution. So that means that when I'm in this distribution, I still and I apply my chain. So I move with my Markov chain. I'm still in this stationary distribution. So you see, this is this relationship. We can observe. We can obtain this mu. The traditional way is to do linear algebra computation. So by solving this equation. But there is, you can also imagine that in fact, what's happening is that when I let my chain going forward in time, So if I compute the power of A, different powers of A, then each row of this chain will converge toward this stationary distribution. So what does it mean in practice? It means that those Markov models, which are only defined by taking by conditioning, so there is an influence on the context, but which is just from one event to the next. In fact, if I let them move and develop in time, after a long time, after some time, we will forget from where we started. Okay, so we will see that when we take power of AK on the exercise. So it just means in practice that those Markov chains, they have a short-term memory. So the state in the present will not influence the distribution in the future. And it depends on the number of states. But when you have only a few, up to a few hundred states, those chains, they converge really rapidly, because you see we take power of a matrix here, so the convergence is exponential. So we forget about the past quite fast with those Markov chains. And that can be seen as a problem, because of course we cannot take into account long-term dependency between events, but that's what is making the computation doable also with that as well. Okay, so that's a little maybe theoretical like that, but we'll see with an example what's the interest of this type of distribution. It just means also if I'm just simulating a sequence with a Markov chain, so I start from any point. We could retake the example of the maze, and we take out the cat and the cheese, and we just follow the mouse. We just follow the mouse in the different rooms. Okay, so in this case, the mouse is just traveling all the time. In this case, our chain is aperiodic and irreducible. And what I just said, what is telling us is that if I let the mouse moving along, and like so I just wait and I let her move for 10 rooms, 20 rooms. So yeah, and I check now where she is. The probability of the mouse in each of the rooms doesn't depend on where the mouse started in the first place. Okay, she could have been in room 1 or in room 3. That will not change. That will not have an influence on the probability where I will observe the mouse. It's just where the mouse will tend to be the most often. And so I didn't solve this question, but maybe the mouse will be most often in room 5. But that's the point, and that's the let's say the interesting, a very interesting property of the Markov chain is to have this stationary distribution. So to know, we just specify. We just have to specify behavior from one step to the next one, but we have let's say long-term behavior which allows us to see which states will be used the most often or not. Okay, so I wanted to show a very, very famous example of this application, the application of this property that you maybe know. In fact, it's the page rank score of Google. So I don't know if you learn how page rank is working. Do you know, Emmanuel and Julian? You know little the idea?
Yes.
So, yes. So you get so you know the point. So yeah. It's called page rank because it doesn't have anything to do with web page. It's the name of one of the two authors. Is how when we do a search on text, how can we rank the page which are going out from it? And so one of the first way of doing would be to take the number of pages which are linking to the page as the ranking. You will take the number of pages linking to the web page. But that's not so relevant, because you could just create a lot of false websites which will be linking to it. So the idea of Larry Page was to say, okay, let's do a more let's take a simple model and consider we would have a random web surfer that will just crawl the well at random, exactly like our mouse, and it will follow from each web page, it will follow the link in proportion, each link in proportion of the number of links going from it. So it's exactly like our mouse, except that a web page is now, a room is like a web page, and the links are all the rooms the mouse can go from. And the idea of a page rank is just that if a web page has a lot of links going to it, it should have a good page rank. And if a web page is referenced, is linked from by other pages which have a lot of links going to them, they should also have a good page rank. Okay. And so you see now, when I look at this case, we have a Markov chain. And what is the page rank? This is just this score is just the probability that the surfer going at random will land on a page. And this is exactly the stationary distribution we were talking about. Okay, so it's exactly what they compute is this property of a Markov chain, like the behavior of this big website, which is seen as a Markov chain. Okay, and so that's just the idea, which is, I mean, you see, relatively methodologically, like the core idea is methodologically simple. Of course, you need to have that working on a huge state space like the World Wide Web. So you need to be able to pile up a lot of other numerical tricks. So we will not get into the detail now, and that's well documented. But that was a good, very lucrative way of, I would say, using Markov chain property. And just to detail, there is in practice still some problems. So we can have pages which are dead ends. So exactly what we saw, so absorbing states. And we can also have parts of the internet which are completely disconnected. And so as we just saw before, we need a chain which is well behaved. And those are exactly cases where the stationary distribution will not work perfectly. So to alleviate that, what they do, they also say at each step that this random web surfer, it follows the link, but it can also do just a reset and just land on any page. In 15% of the case, it will just jump to any other possible page. So this parameter of 0.15 is the parameter used by Google, and they must have set it according to some data, but I didn't find details on why it's 0.15. Okay, so let's just go through a simplified example on one internet web site with 5 pages. So P1, P2, P3, and with 4 pages. I don't know why I wrote 4. Okay, with 4 pages, P1, P2, P3, and P4. And so you see it's the graph of a link. So if I'm in P1, I have 1 chance out of 2 to go to P2 and P3. In P2, I just go to P3, P3, P4, P4, P3. So very simple web page. So we can write our transition matrix. First, we encode the structure of our internet here with a probability. You see, from 1, I can go to 3 and 4 with same probability, etc. I put this normalizing constant, 0.95, and then I have the random reset. 1 chance out of 4. From each page, I can go to all the other page with 1 chance out of 4 times this normalizing factor. We combine everything in a matrix, and our matrix is like that. And then we can either diagonalize, use a linear solver to find the stationary distribution, or take power of t, and we get our page rank, which is just the probability of being in each of those pages for the random web surfer. And we see that the highest page rank is for page 3, which is kind of expected. You see page 3 as is the one where the most links are going to it. So this will be the most, the one which is the most looked at. And the second highest page rank is page 4, which gets high page rank as being a page linked by page 3, which has already a high page rank. So that kind of satisfies the idea that was behind page rank. But I mean, that's the idea, the way they presented it, but you see that from a model point of view, we can just think about another Markov chain. And so from the Murphy book, I just wanted to show like a little, slightly bigger example of a web structure that he got from the sites which go from the Harvard web page. And you can see that there are like some clear structure in terms of a link. So there are like 500 sites. And you can get the structure of, you can plot the structure of this transition matrix, 500 times 500, and also computing the page rank for those different web page. Okay, so it's just to get a view on that. So the project that we will do, it's exactly, in fact, it's also the same on a simpler setup where we look at the monopoly. And you know, in the monopoly, you start from here, and then you throw 2 dice, and you can move according to the dices. And so the movement of how do you call that? Each person which is playing, its movement is just decided by the dice. But there is a strong, very important case, which is this case: when you land it here, you directly go to jail. And so it's like, it's not a random web surfer, but when you play Monopoly, you have a huge part of Monopoly is a randomly moving, I don't know how you say that in English, randomly moving person on the different case of the monopoly. And so that will be, I think, a good way of setting up a simple Markov model, but using, I mean, it's still a lot of states, so it's nice to have Python, or let's say a computer to manipulate that. And that will be a good way to illustrate what is the stationary distribution giving as information. Okay, so there was a last point I wanted to make, is how do we estimate the parameters of a Markov chain? So when we observe sequences, and that's the important thing, of course it's an important thing. So as you remember, the probability of a sequence with a Markov chain is it looks a lot like the probability of independent sequences. Instead, that with independent sequences we just take the product of atomic events. Here we have a product of a succession of events. Okay, so I just recall here the probability of a sequence. It's probability of the first event times the probability of going from previous to next, the product. So if we take the log of that, you see we have a log of this first probability. I forgot to log here. Come on. Plus the sum over all the position of the log of moving. So it's a probability again, moving from xa minus 1 to xa. So we can do exactly like we did for Multinouilly or for Bernoulli. You know, we counted how many times I observed each event, and the sum which was on position here, I would just do that on a possible state. And we can do the same here. We don't enumerate states, we enumerate pairs of successive steps. And we can see, so I mean, you can maybe write that to be sure on your own, but you can see easily that then it's just the log likelihood, it's just the log of this the first element plus the sum over all the pairs of states of the number of times I observe A followed by B times the log of this, and this is the parameter we want to estimate. And you see we again get back to this ponderated sum of log of our parameters, where we saw that the maximum of this function is obtained when I normalize the count I have here by the sum of the marginal counts. And so this was just to show that to to get to the idea that very intuitively, the estimator of our Markov chain, the maximum likelihood estimator, if I want to know the probability of going from A to B, very intuitively, I just count how many times I went from A to B, and I divide by the number of times I was in A and I went somewhere. And that's our estimator. Okay, so as a summary, we just went through the Markov chain model, let's say, relatively rapidly, but I think it's mainly a matter of manipulating those models and understanding in which case that they are very practical to approximate sequential data or sequential sequences of events. The main one of them, it's not a limitation, but one of the main property that is used often is that those Markov chains, they will converge to a distribution, and they converge quite fast. So we have this short-term memory, which can be a problem when we want to model a little more complex event. But we'll see for in the next course is that when we combine those Markov process, so those dependent process as latent variables, they will prove very, very powerful in being able to analyze sequences of events. And those are like hidden Markov models that we will see for the next in the two next courses. Okay. And so the project, as I said, this will be the monopoly. Okay. So this was the course. How can I wait 1 sec. I just want to, here, okay. I want to stop recording.